In this video, we will continue our exploration of determining what the bending stress is for a given applied moment for a particular cross-section. And so what this question is asking us is that what bending moment applied about either the x or the y axis would generate a bending stress of 300 MPa at the extreme fiber. So if we're bending about the xx axis, the extreme fibers will be the top and the bottom of the cross-section. And if we're bending about the YY axis, the extreme fibers will be these edges of the flanges. So in order to get started, what do we need to do? It's always good to sort of try to set up our governing equation. And so if we're looking at bending stress, our governing equation is simply going to be sigma equals the applied moment times y over I. And if we care about the extreme fibers, then really this y will go to y max. So sigma equals m times y max over I. And where y max is going to be the maximum distance from the neutral axis. From the neutral axis. All right, and so with all of that, effectively, then we can do some rearranging of really all we're trying to find is this fx. So if we want a bending stress of 300 MPa, so if sigma equals 300 MPa, we can just do a little bit of algebra and a little bit of substitution. We'd find that 300 MPa times I over y max equals m. So there we go. Really all we need to find in order to find either this max moment mx or my is really just what the moment of inertia about either the x or the y axis is, depending upon which one we're looking at, as well as this max distance away from the neutral axis, y max. So I guess with that, we can just sort of get started in. So let's start with, finding the maximum moment about the xx axis. So the first thing we need to know is, obviously we've got a symmetric cross-section with a depth of 250, and so we need to find the centroid, and that's just simply going to be half the height. Y bar equals d over 2 equals 250 over 2 equals 125 millimeters. And so obviously I'm just taking advantage of the fact that this is a symmetric cross-section, and I know it's going to be right in the middle. If you had an unsymmetric cross-section, you'd have to work out what the centroid was from the first moment area. But the other thing that we need to know is that our centroid for bending stress is always going to be the location of our neutral axis. And that's good. And so if we know the location of the neutral axis, well, then we can work out y max, which is the distance away. For us, this will be effectively the same, because if our centroid is located right here at 250 millimeter, at 125 millimeters up from the base, well, there's 125 millimeters to either extreme fiber, so that's going to be what our y max is. All right, so and moving on, let's work out what our moment of inertia is. And to do this, we'll use the parallel axis theorem. in which I total is simply going to be the sum of I sub I plus A sub I di squared. All right. So if our moment of inertia is effectively going to be this I section, well, we can break it out into some smaller constituent pieces. So we'll just draw this out graphically first, because I always find that's helpful. And so if we're going about the XX axis here, this is simply going to equal the outside, which has a width of 150 over 250. And this distance here, 125. Subtracting out really the two voids either side of the web here, so these two. So minus the void. So we'll sort of dash in the I section. And it's these two pieces here, which have their centroids also located at the same location as the centroid for the entire cross section, which is 125 y bar, and this too 125. And then let's just go ahead and color in the areas just to make it show up nice and clear in the video. Alright, so with that, and then we'll also put some dimensions here. So this is 70, and it has a height of 218. Just 250 minus 2 times 16. Alright, well, let's work out what that moment of inertia is. So our total moment of inertia is simply going to be 1 over 12 times 150 times 250 cubed plus 150 times 250. And then our distance of this whole block to the centroid of the whole thing is going to be 0 squared, so that goes to 0. And then it's going to be minus 2 times these, the voids, which is simply going to be 1 over 12 times 70 times 218 cubed, also plus 0, because the distance between the centroid of these voids and the centroid of the whole thing is 0. Alright, so if we have all of that, we work out that IXX equals 7.44 times 10 to the 7th millimeters to the 4th. And so if you've got any trouble finding that, just go back and review on the examples that we have on determining the moment of inertia using the parallel axis theorem. But now, I guess what we have, well, we know y max is going to be 125. We know our moment of inertia. We know our stress. So we can simply work out what mx needs to be. So mx, which will generate a 300 megapascal bending stress at the extreme fiber, is simply going to equal 300 MPa times I over y max equals 300 Newton per millimeter squared times 7.44 times 10 to the 7th millimeters to the 4th, all over 125 millimeters times 1,000 newtons per kilonewton times 1,000 millimeters per meter just to get us into kilonewtons and meter. And if we run through all of that, we get that mx equals 179 kilonewton meters. All right, well, that seems pretty straightforward. Well, we've got the first bit where we've worked out, what moment about the x-axis would generate a 300 megapascal stress. So now let's look at going about the y-axis. So if we were to do that, again, let's look at just getting our paper rearranged here. So for B, my, which is the moment about the y axis. And so if we're drawing our y-axis down the centroid, well, we know, again, just through symmetry, that x bar equals 150 divided by 2 equals 75 millimeters. X bar equals, we'll call this y max, equals 75 millimeters. So I'm using y max just simply because, this equation here, we're using y because we usually bend about the strong axis, the x axis of a element. However, there's nothing to say we can't, it doesn't also hold true bending about the opposite direction. So we could call this, x max, but y is really just whatever distance away from the neutral axis that you are bending about. And so because we're bending about the y-axis, it's going to be the maximum distance away from there, and that's going to be 75 millimeters. All right, so let's work out what our moment of inertia about the y-axis is. And that's simply going to be, well, again, we'll draw it out graphically. So our total moment of inertia is simply going to be the moment of inertia of the web and put some dimensions, so that's 10 millimeters by 218, and then plus the moment of inertia about the flanges. And because each of these elements has its own centroid aligned up with the centroid of the entire element about the y direction, our parallel axis theorem means that d squared term just goes to 0. So that's always handy. And again, some dimensions here. We have 150 and 16. All right, so we'll go ahead and just sort of write out what our parallel axis theorem would be. So I total equals the moment of inertia about the y direction of the web plus the area of the web, d web squared. And again, because that distance is exactly at the same location as x bar, in fact, we'll just go ahead and just put down 75, 75, 75, just to show explicitly that that's 0. So that's going to go to 0. plus 2 times I y flange plus a flange d flange squared. And again, the centroid of the flange is lined up, right about the centroid we are circling around, so that's going to go to 0. So what we end up with is Iy is simply going to be the moment of inertia of the web plus 2 times the moment of inertia of the flange about the y direction. And that will give us 1 over 12 times 218 times 10 cubed plus 0 plus 2 times 1 over 12 times width of 16 times 150 cubed plus 0. And if we plug all of that in, we get Iy equals 9.02 times 10 to the 6th millimeters to the 4th. And so now if we've got what our y max is, and we have I, and we know the stress we're trying to get to, we can determine what my is. So my equals stress Iy over y max equals 300 MPa times Iy over x bar equals 300 times 9.02 times 10 to the 6th millimeters to the 4th over 75 millimeters divided by 1,000 divided by 1,000. And then that will give us, if we turn all of this through, we get my equals 36.1 kilonewton meters. And there you go. So hopefully you found that actually a fairly straightforward process. Like the hardest thing is effectively just working out what direction you're moving around, determining your moment of inertia. But once you have that, it's really just some manipulation of our general bending stress equation of stress equal the applied moment times the distance away from the neutral axis over the moment of inertia. So, as again I say, I hope you found that helpful and informative, and I'd like to say thanks for watching.